here today to listen to, maybe from here, the talk from Andrew Bunker. And so Andrew is a professor at the University of Oxford, UK. And before this, he had a quite interesting story. He was head of the astronomy of the Anglo-Australian Observatory in Sydney. He had a position at the Exeter University. Even before, he was a postdoctoral researcher at the University of Cambridge and also California, Berkeley. And at the origin, he was raised as an undergraduate and postdoctorate at the University of Oxford. So that's where he came back 2 years ago, I guess. And Andy is on his instrument team for NIRSpec and in the steering committee of the JADES program that you know. And he is also an editor of MNRS. And Andy's research is focused on galaxy formation evolution and the search for the highest redshift galaxies. So please.
Many thanks, Denis, for that nice introduction. And it's a pleasure to be here. Many thanks for inviting me. So I'll talk today about James Webb results, specifically things from the JADES collaboration. This is a collaboration between the NIRSpec Instrument Science Team and the NIRCam, the spectroscopy and the imaging sides of James Webb. And in particular, I'll focus on the high redshift frontier, what we can learn about the earliest stages of galaxy formation. So I know there are a number of graduate students in the audience, and you've started your research lives after the launch of JWST. But I just want people to cast their minds back 4 years ago, before JWST results started rolling, and remember how primitive high redshift research was back then. So I'll sketch out the main developments over the previous 30 years or so. So in the mid-90s, Chuck Steidel and his colleagues developed a very neat technique called the Lyman break technique to identify potential distant objects. So this yellow cartoon spectrum up the top, this is a distant galaxy, and you see, you get this weird picket fence-like absorption, and then the flux dies away. Here, this is absorption by clouds of neutral hydrogen. Yeah, the pointer's not working, but yeah. Along the line of sight between us and the very distant galaxy. And that erodes at Lyman alpha, the resonant.
Sure. There is a stick.
There's a stick. Old school, yeah. 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 So where the light passes through these clouds of hydrogen, that absorbs at the resonant wavelength, and that erodes the flux. And then shortward of the Lyman limit, the ionization edge, it's basically illegal for any photon to get through. The universe is optically thick. So if you put a filter here, a galaxy will vanish if it's high redshift. But if it's lower redshift, everything shifts to the left, and you still see the galaxy. So this technique was a way to slim down your list of potential high redshift objects. So you might think naively, just take a deep image and pick the faintest ones. But because there's a luminosity function of galaxies, if you do that, typically you'll get a low luminosity galaxy in intermediate redshift. You need more information, and that information comes from the broadband colors. And Chuck Steidel and his colleagues then followed up in the mid-90s and showed with spectroscopy on Keck that these were indeed galaxies at redshift 3. And then they pushed that to redshift 4. And other groups, my own included, pushed to higher redshift. So to do that, you simply shift this yellow spectrum further to the right at high redshift, and you see it vanish in progressively redder filters, and it gives you an estimate then of the redshift. But unfortunately, the spectroscopic confirmation gets harder at high redshift. First of all, they're fainter. Mainly, the flux shifts to longer wavelengths, and the spectroscopic capability really runs out of steam from the ground around the K-band at 2 microns, but with great sensitivity in the optical that runs out at much shorter wavelength. And we were restricted to just taking spectroscopy in the rest frame ultraviolet. And it turned out that either you got Lyman alpha in emission, rarely, or the other lines were too faint from the ground. So we were stuck that beyond around a redshift of 6 or 7, very few of the candidate distant objects had confirmation. So people like me, for 20 years in our careers, we were counting red blobs in Hubble Space Telescope images. We were going around to conferences saying these are likely to be very distant objects. Can't prove it because we don't have a spectrum, but they're likely to be. And on the basis of we're confident, we've assembled luminosity functions and we can say something about the evolution of the universe. Now, of course, rightly, people said, well, we want a bit more proof. So what came out of these efforts up until JWST was the star formation history of the universe. So remember that those red blobs I showed you, if they are high redshift, we were sampling not the red, but in the rest frame, the ultraviolet. So this is highly sensitive to star formation rate. We were able to estimate the volumes we surveyed, the depths to which we reached, and we were able then to put points on the right-hand side of this plot based on the rest frame ultraviolet, converting that to a star formation rate, the UV coming from the very short-lived but massive stars. Fine, but there are uncertainties. One is dust. The other one clearly is we don't have the spectrum. How do we know they're high redshift? At the low redshift end, people use a different diagnostic, H-alpha, which more directly probes Balmer alpha, the ionizing production rate, and therefore, if you assume an IMF, the star formation rate of distant galaxies. So the left and right parts of the plot, by necessity until JWST, were done using different diagnostics. Now, you might well feel uncomfortable, as the community did. Different diagnostics, how do we know the shape is real? And then this green area on the right, which I've highlighted, this becomes particularly interesting because this is the epoch beyond redshift 6. That's the first billion years of history, where we know the gas between the galaxies, the intergalactic medium, undergoes a phase change. It goes from being mostly neutral to being mostly ionized. And then the question is, what source of ionizing photons achieved that? Was it AGN? Was it star-forming galaxies? If so, was the high luminosity or the low luminosity ones? And there's good direct evidence from reionization from the spectra of distant quasars. We see the so-called Gunn-Peterson trough beyond a redshift of 6 or so, where the universe was neutral. Also complementary evidence from the CMB. But the question, I think, to this day remains still, what caused this? And JWST has made some advances. So just to recap the ancient history of this field before I get on to James Webb. For 30 years, the Lyman break technique has been successful in identifying candidate high redshifts. And these have been confirmed out to a redshift of 6 or so, with a handful then confirmed from the ground out to redshift 8, but just a very small fraction. Why so few? Well, the problem is we're looking from the ground sensitively at the rest frame ultraviolet. The strongest line was expected to be Lyman alpha, the fundamental transition of hydrogen from the first excited state to the ground state. The predictions going back to Partridge and Peebles in the mid-60s said this was going to be the brightest line. Everything's hydrogen, ionizing photons, there you go. But in the late 90s, it became clear this line is only seen in emission, and often weakly, in about half the galaxies, even those that we know are actively star-forming and creating a lot of ionizing photons. Why is that? Well, it's because Lyman alpha is resonant. You can imagine one of these photons propagating through a cloud of neutral hydrogen. Whenever it encounters another atom of neutral hydrogen, its capture cross-section is enormously high. So it scatters around, it plays cosmic pinball on the way out of a slab of neutral gas, extends the escape path very greatly. If there's any dust at all, that can quench that line. So resonance scattering effects mean that this line, expected to be the strongest, in fact, turns out typically to be very weak. And if you don't get that in the spectrum, there's not that many other bright features in the UV. Now, ALMA did some heroic work on a small number of galaxies before JWST, typically getting the carbon-2 line, 158 microns, out to high redshift, but in a small number of cases. But really, we were stuck. We got a lot of candidates at redshift 6 and beyond, thanks to deep imaging campaigns with Hubble, things like the Hubble Ultra Deep Field, wider area things like Cosmos, like the Goods fields. But we were stuck because we could not spectroscopically confirm them. Then the game changer was the James Webb Space Telescope, and this has 4 instruments. MIRI, the mid-infrared, I won't focus on that today. Canada provided the fine guidance sensor and a slitless spectrograph called NIRS. But the 2 instruments I want to focus on, NIRCam, the imager, out to 5 microns, that's built by University of Arizona, and NIRSpec, the near-infrared spectrograph, built by Astrium under European Space Agency. And since 2005, I've been on the Instrument Science Team for NIRSpec. And when I joined the Instrument Science Team, we were still building NIRSpec at that point. In 2005, we were told we were 3 years before launch. That 3 years actually telescoped into 16 years, but it did eventually launch. I'll tell you a little bit more about NIRSpec in a moment. But I just want to preempt some of the results later on. So a lot of what I'll show is done with my team in Oxford. It's funded by European advance grant, and I'll introduce the work of the various members as we go through, but I'll just show their faces now. And NIRSpec, the near-infrared spectrograph, it works between about 0.7, 0.8 microns all the way out to 5.3 microns. Now, why this is critical is these are the familiar lines, the rest-frame optical, H-alpha, oxygen 3, oxygen 2. You can see these out to enormously high redshift. H-alpha out to redshift 7, O2 potentially out to redshift 12 or so. And if you look at the rest-frame ultraviolet lines, things like Lyman alpha, which I've mentioned already, a couple of lines of carbon, you can see these out to potentially ludicrous redshifts. Now, when we created this plot, we thought this was a joke. There's no way we'd see these out to redshift 13 or 14. But we have. So, and I'll show you that result later on. So, the NIRSpec has a number of observing modes. Sorry, just one second. And a number of spectral resolutions. So we go from low dispersion, the prism, where we get everything at once. So we see all the way from 0.7 to 5 microns at one shot, but at very low resolution. So this has become the workhorse. We're incredibly sensitive. Things down to 29th, 30th magnitude in AB units. We're able to take a spectrum and get a redshift. Then we have higher dispersion gratings. Those are particularly useful for separating lines which are blended in the prism, for example, nitrogen 2, H-alpha. Also running at R of 3000, that's 100 kilometers per second, we're able to do kinematics of galaxies. But you have to do several observing modes, typically 3, to cover all the wavelength range with that. So the prism, you get everything at once, is very efficient in observing time. Now, it has different observing modes as well, not only in terms of resolution, but in terms of sampling and field of view. So there's an integral field spectrograph mode, where essentially you carve out a 2-dimensional area of the sky, 3 by 3 arc seconds, and you get a spectrum at 900 independent points over that galaxy. So that's great for rotation curves. It's great for measuring metallicity gradients. It's great for looking for evidence of mergers. What I'll focus on today is the top mode, which is multi-object spectroscopy, where you can take a spectrum of a couple of hundred galaxies at one shot. So this really is revolutionary. So with Hubble, that does have slit spectrographs, but you're restricted to one galaxy at a time. Building a slit mask in space and stacking your spectra up so they don't overlap enables you to get very much deeper. Now, you might think, well, in space, there's no sky background. Why don't I just do slitless spectroscopy? The sky is faint. I get a spectrum of everything at once. And indeed, that mode is available, the NIRS spectrograph, built by Canada, also a mode of NIRCam, slitless spectroscopy. But it's not true to say there is no background in space. There's zodiacal light, there's scattered light in the instrument. So by building an apodized slit mask, like we do on Earth, slit masks and fiber fed, you're able to cut down the background light and become incredibly sensitive. So that's the point of NIRSpec. We have a multi-object mode called the microshutter array. We have 1/4 individually addressable microshutters that you can command to open or close in space. This means that you can build your own slip mask. Now, the golden rule of anything to do with space-based is have as few moving parts as possible. We ignored that. We have 250,000 shutters that can open and close, but no one of them is a single point failure. And it works very well. So you could either command your shutters, as we've done here, to build your favorite space agency logos, or perhaps more usefully, command them to open on your candidate high redshift objects. So you're getting, typically with a prism, a couple of hundred at once. So we use this mode to address some big questions. And don't worry, I'm not going to answer all of these today. This is just to frame some of the discussion. So we're interested in the history of star formation. How rapidly does the universe turn its gas into stars? Interested in how this is divided among the galaxies. And also the production of heavy elements. Hydrogen and helium were built in the Big Bang. Anything carbon and heavier is made in stars, made in supernovae. Can we monitor the individual element abundances as a function of redshift, as a function of time? And also I've touched on what is the ionizing budget of the universe. And the fundamental question, all these high redshift candidates that were kicking around in some cases for decades, can we actually confirm them that they really are high redshift to understand it? So with that in mind, the NIRSpec Instrument Science Team combined forces with NIRCam. Now, as instrument science teams, we had a lot of guaranteed time hours, and we thought rather than salami slicing this to do 20 different topics in astrophysics, let's just concentrate on galaxy evolution, do a big survey, and have some impact. So we came up with the JADES survey, that's the JWST Advanced Deep Extragalactic Survey. And here's just, I think, a subset of the team on a rainy day in Oxford. There's more than 100 on the team now, split between NIRCam and NIRSpec. And we've been working, our first data came in, I think, October 2022. And we've been pretty successful, over 100 papers so far. And one of the reasons why we're able to cooperate so well is NIRSpec is so sensitive that going in, the only patch of sky that was imaged deep enough to give us enough targets to hit in an efficient way was the Hubble Ultra Deep Field. If you cast your mind back, that was first imaged in 2003, 2004 with the Advanced Camera for Surveys, later on with the Infrared Wide Field Camera 3 on Hubble. And that reached depths of perhaps 29th magnitude. And that gave us a sufficient target density of galaxies beyond redshift 6 to nicely fill the array. But that was one field. So in order to get more targets, we needed the depth of NIRCam that goes very deep very quickly. So this was a collaboration between NIRCam to get us the targets and NIRSpec, the instrument that I'm involved with, to do the spectroscopy. And this is the focal plane of James Webb. So as you image with NIRCam, you can take some deep spectra with NIRSpec. And then later on, you switch round such that you're hitting the new targets you've found with NIRCam later on in the cycle with NIRSpec. So this proved very efficient. And we hit the two goods fields, goods north and goods south. So goods north is around the original Hubble Deep Field, goods south around the Hubble Ultra Deep Field. And these were enormously well studied. And you might think, well, why are we bothering with HST fields? JWST goes so much deeper, so much more quickly. HST is crucial, provides the short wavelength. So James Webb doesn't have much sensitivity below 0.8 microns. In order to identify the dropouts, we need imaging in the visible wave bands. Also, there's so much ancillary data, in particular X-ray data, and in the south, ALMA data, and also radio data, particularly in the north. So this means that we were able to pick out unusual objects to hit, such as AGN as well. So we hit the goods fields, and we had our first data release, 2023, which I led for NIRSpec. So this is an almost science-free plot. All I've done here is stacked up. We had 250 spectra from low redshift down the bottom to high redshift at the top in order of redshift. So you see these emission lines. This is H beta and O3. This is H alpha. They shift to the right, to higher redshift, longer wavelength as you go up. And if you squint a bit, you can see this drop in the continuum level to the left. That's the famous Balmer break, or 4,000 angstrom break. And then it goes dark here, and that is the how we select a lot of these galaxies. That is below the Lyman alpha, where the gas between the galaxies absorbs. That's the Lyman alpha dropout. So since then, we've had a couple of data releases. The final one for NIRSpec came out last October, led by my colleague Emma Curtis-Lake, my postdoc Alex Cameron, and me. So here we have now 5,000 spectra. So this is the final release of JADES spectra. And you see not only has the color changed from brown to green, but we have many, many more galaxies. And you can see this beautiful Balmer break here, Lyman alpha break, and all these emission lines, including the passion lines at low redshift. So there we're able to really look at things like the shape of extinction curves. Just to impress on you how much of an improvement this is over Hubble. Hubble only showed that part of the spectrum out to 1.6 microns and much less deep. So suddenly we have access to the rest frame optical out to ridiculously high redshifts, 95% of the way back in time of the Big Bang. Multiple emission lines to do diagnostics, to do star formation rates, to do metallicities, to do AGN selection, for example. Now, like most surveys, we've structured this such that we do a couple of pointings going extremely deep, probing down to 30th magnitude. And we get the faint galaxies there. But then we want to capture the rarer but brighter sources, so we do wider area as well. So we have various different tiers, medium tiers, deep and ultra deep. And you can see here, this is the redshift histogram. So in the ultra deep, we're going out to redshift 14 or so. But in the medium tiers, typically we go out to redshift of 7. And we do a good census of galaxies down to the cosmic noon, they call it, redshift 2 or so, when a lot of the stellar mass is being assembled. So it's not purely a higher redshift sample. We're interested in galaxy evolution as well. So the first time we observed, which was the autumn, the fall of 2022, we broke the redshift record 3 times in our first set of observations. So these 4 galaxies here are redshift 10 and beyond, 3 of which broke the existing redshift record. So what I want you to notice, these yellow things, this is the continuum flux. And wavelength is along the x-axis, and all of these seem to vanish below about 1.5 microns or so. And that is because of the Lyman alpha break. So we've confirmed through spectroscopy it really is a continuum break. It's not some weird pattern of emission lines contaminating broadband filters. Now you might look at this and think, well, yeah, that's impressive. You've broken the redshift record. Don't see any emission lines. Is this because you found population 3 and the metal emission lines don't exist because there are no metals? Sorry to dampen your enthusiasm about that result, because our initial data was 19 hours, and we decided to hit some of these again, going to a record-breaking 65 hours. This is the deepest spectrum, I think, obtained so far ever in the universe. And one of these galaxies I showed on the previous plot, if you go to 65 hours, you start to see lines of carbon, lines of nitrogen, oxygen, and clearly this is not a population 3 galaxy. So this is interesting. This is redshift 12.5. Not a lot of time after the Big Bang, 300, 400 million years. Already we have heavy elements in place. Now, my colleague, Francesco De Eugenio, led a paper on this as part of JADES, and he plotted the abundance in oxygen on the x-axis versus the carbon over oxygen ratio on the y-axis. What's interesting, our redshift 12.5 galaxy is up here, and that doesn't fit with a lot of what you expect for population 2 element abundance ratios. Clearly, we've not seen population 3 directly. We have the metal lines. Population 3, first generation galaxies, supposed to be metal free. But Francesco in the JADES paper suggests that in fact the abundance ratios are such, because we have an elevated carbon over oxygen ratio in this particular galaxy, that this is consistent with pre-enrichment from population 3 supernovae. So no population 3 yet from this galaxy, but hints that we are getting close to the first generation of stars. So until a few months ago, this was the most distant galaxy spectroscopically confirmed from JADES, and this was a redshift 14 galaxy led by Stefano Carniani. Now, at the top, what we're showing is filters going progressively redder. So this is the I band at 0.9 microns, effectively the K band at 2 microns, and then all the way out to 4 microns here. Notice this blob on the right. This seems to vanish at 1.5 microns and below. That is the Lyman break. Now, when we identified this galaxy in the imaging, we were highly nervous because, you know, notice there's a blob on the left that exists at all wavelengths. Clearly, that cannot be high redshift. You know that. And what are the odds of a high redshift galaxy being that close to a low redshift galaxy? And we were nervous. We thought, well, maybe it's a dusty star-forming region associated with this galaxy. But we put a slit on it anyway, and we were glad we did, because we showed indeed this is redshift 14. You see here the Lyman alpha break. You see hints of an emission line here, which we didn't fully believe at the time, but I'll show you evidence this is real. This is carbon-3 at a redshift of 14.2. So very impressive. Unexpected. One of the other reasons we were nervous about putting a slit on it, if you work out the luminosity of this galaxy, it's very much more luminous than you would presuppose a redshift 14 galaxy should be, given the volume we surveyed. Now, it seems now this is a true result, and others have found, although JADES first discovered this, others have now found other galaxies which seem to be overluminous in the UV. And there's a whole debate about why this is. If you work basically on the Hubble results, it seemed that galaxies were getting fainter, fainter, fainter as you got to higher redshift. And the star formation density of the universe seemed to be dropping following that McDowell-Lilly diagram I started the talk with. So what's going on at high redshift, at even higher redshifts, 10 and beyond? It seems that there's some mechanism to make these galaxies brighter. Could it be they are more massive? That would break cosmology, and there was some very excited headlines a few years ago. That's no longer believed, but there's some mechanism where the UV flux is elevated. It could be things are more bursty. It could be that the initial mass function is top heavy. It could be just there's a different mode of feedback going on early on. So this is great because it was not predicted theoretically. This is an observation, and now people are struggling, or struggling is the wrong word, rising to the challenge of trying to address this. So I'll just comment on the nearby neighbour. What happened to this guy that was clearly low redshift? We also took a spectrum of that, and that is clearly redshift 3.5, not at redshift 14. We never expected that. But we were, you know, very lucky because its Balmer break almost mimicked the Lyman alpha break at higher redshift. So we were almost convinced that our high redshift candidate would not be high redshift. I mean, coincidence, but it turned out it was. And it's been confirmed through Almer observations, both by the JADES team, led by Stefano Carniani, but also by Sander Schauls, using the same data, showing an oxygen line at exactly the right redshift. So this is great. We have two elements now, a redshift 14, confirming that galaxy. So this is showing what I said a couple of minutes ago. This is redshift going here for our sample, the lower redshifts, redshift around 8, all the way out to some candidates at redshift 16, as yet unconfirmed. The things with circles have been spectroscopically confirmed by NIRSpec in JADES, and but also a few other surveys as well. Now, what you note, this is UV magnitude here. So up the top is bright, down the bottom is faint. So there are selection effects going on, of course, but this cloud up here are very UV bright. And that is the mystery at the moment. At the highest redshifts, why are these so UV bright? Our selection should include much fainter sources as well, but it seems that the number density of these high luminosity systems is surprisingly large. So how did we choose these sources? We chose them through the Lyman break technique, also through photometric redshifts, where you add in more information, you make an estimate of the redshift. And part of the goal of JADES is to test photometric redshifts. So photometric redshifts, I know a lot of people here work on that. You put in templates, what is the best match in terms of redshift, moving this to longer wavelengths. But you worry, are your templates accurate at high redshift? These are templates typically from low redshift starburst galaxies. We don't know whether they hold at high redshift. Well, we do now because we're able to take the spectra. So one interesting thing, if you plot spectroscopic redshifts, this is truth down the bottom, versus your photometric redshift estimate, maybe you notice that they all, the photometric redshifts always seem to be biased slightly high here. Now, we believe that is the case because the optical depth of the gas between the galaxies, the Lyman alpha forest, and also damp Lyman alpha systems, that's slabs of neutral hydrogen associated with the galaxies, erode the continuum of flux towards the Lyman alpha break. So it's so-called damping wing. And when we correct for that using a recipe in the literature, we get a much better agreement. You can see on the right the photometric redshifts come into alignment. So it's not so much a template issue as accounting for the Lyman alpha absorption of the IGM and the galaxy itself. So that's interesting. Initially, I showed you the Medal-Lilly diagram. I commented at redshifts beyond 2. Most of those data points for the volume average star formation rate relied on luminosity functions being integrated, but those luminosity functions, we didn't have spectroscopic redshifts of the galaxies going into them. We now do, and my postdoc Alex Cameron, in the paper led by Emma Curtis-Lake, Alex's key role in this, as well as being largely responsible for the target selection, he recovered the luminosity functions based purely on spectroscopic redshifts. So those are those green points on the right plot. And they actually agree rather well with the luminosity functions obtained purely from photometric redshifts. So that's telling us the templates are not so wrong. Estimates of the volumes covered, etc., were not so wrong. So that's reassuring. In my the second half of the talk, I'm going to tell you about the physical conditions in high redshift galaxies. So hopefully I've convinced you we're able to get redshifts all the way out to redshift 14. Certainly now a large sample, redshift 6 and beyond. What can we tell you about galaxies now in the first billion years of history? So Alex Cameron, until recently my postdoc in Oxford, now at the Dawn Centre in Copenhagen, led an early paper where he looked at the emission line ratios, effectively the rest frame optical lines, and how those evolved. So a little bit of a complicated plot, but the x-axis here, this is a proxy for metallicity. This is the R23 diagnostic that involves the oxygen 3, oxygen 2 lines, and H beta. The y-axis here, this is related to the hardness of the ionizing spectrum, the ratio of doubly ionized oxygen to singly ionized oxygen. This grey region here, dark region here, these are the Sloan galaxies. This is typically redshift 0.1 out to a slightly higher redshift. Up here, these purple symbols, these are the JADES galaxies. So immediately you can say high redshift galaxies are not like low redshift galaxies. No real surprise, but they are in the sense of lower metallicities and harder ionizing spectra. Low metallicities, of course, that's expected. That's early on in the history of the universe. You haven't yet built so many metals in star formation. Harder ionizing spectra, well, I mean, that could be related to a number of issues. Low metallicity for sure, potentially hints of a different IMF, or certainly a hotter interstellar medium. And also, there are other symbols here. These are lower redshift galaxies which are selected for having unusual properties. There's so-called green peas, blueberries, various other fruit and vegetables. And these are often selected to have intense line emission. I'm going to come back to this point later on. They're not dissimilar to the properties of some of these high redshift galaxies. Now, full disclosure, using these strong lines, oxygen 3, oxygen 2, to measure metallicities is highly uncertain. That people worry because it's it's very sensitive to the temperature of the interstellar medium, also the electron density of the interstellar medium. But we can improve those estimates, and in fact, early on in James Webb, there were indications that these calibrations would greatly improve. So if you cast your mind back to the first ever data release from James Webb, we see here the pretty picture of a gravitationally lensed cluster. So these yellow objects, these are elliptical galaxies typically in a modest redshift cluster. And these orange and red arcs, these are lensed images of galaxies which are much more distant, amplified by the potential well of the cluster. And you can see then President Joe Biden on the press release peering intently into this deep image. And not only did NASA early on release images to the public, which we can all understand, images are beautiful, everybody likes that, but also courageously they released spectra. Spectra are quite difficult to explain to the public, but astronomers got very, very excited because in the public data release that Joe Biden was able to identify an auroral line of oxygen. So what are the auroral lines? These are excited states of the famous, in this case, doubly ionized oxygen. And the fact it's an excited state and the fact that being physicists we know the Boltzmann equation enables us to get the temperature, ratioing that with the ground state. So if you know the temperature, you eliminate one of the uncertainties in converting your brightnesses of emission lines into an actual chemical abundance for oxygen. So the fact that we can see auroral lines is fantastic. It enables us more accurately to determine the temperature and therefore the metallicity of these objects. Now, the fact that these auroral lines were bright tells you something immediately. The interstellar medium, in this case of a redshift 7 galaxy, is much hotter than the interstellar media of low redshift galaxies, which are used for the strong line calibration. So immediately that's telling you something. And my colleague Mirko Kurti, who's led the metallicity measurement effort of JADES, has compared, this is the mass metallicity, so mass increasing left to right down the bottom, and metallicity in oxygen increasing as you go up. This is from Sloan. These are our measurements from JADES split by redshift. So here we see a sample of redshift 3 in yellow, all the way up to redshift 10 in blue, and some other lower redshift samples here. So obviously, as you push to high redshift, the metallicity on average goes down, the universe is younger. But people are interested in the shape of this mass metallicity relation. So it seems that more massive galaxies have higher metallicities, either because their star formation activity got underway earlier, accelerated galaxy evolution, or the deeper potential wells means that they're better at hanging on to their metals. They're not ejected and escape after they're expelled from stars and supernovae. So it's probably a combination of two effects. But complicating that is, of course, inflow of gas triggering star formation, further star formation, also potentially diluting the metallicity. So mass metallicity relation is highly interesting in astrophysics, also highly confusing, but certainly we can say without doubt that it evolves strongly out to high redshift. So I mentioned before, one of the puzzles of JWST is the brightness in the UV of very, very distant galaxies. One of the menu of options to explain this is that star formation at high redshift might be very bursty. This, give them credit, this was something that the theoreticians and simulations actually do predict. How do we actually assess this? So one way of doing that is to look at the intensity of emission lines, for example, oxygen 3 or perhaps the Balmer lines. These are related to star formation activity, particularly in the rest frame optical, comparing that with the strength of the continuum. So the emission lines typically come from stellar populations younger than about 10 million years. But the surrounding continuum, that's sensitive to much longer star formation, older population. So the ratio of these two, which is called the equivalent width, gives you a handle on young stars versus previous star formation history. And my then postdoc, Kit Boyette, did a histogram. Sorry, his image is overlapping the caption, but this is equivalent width in the rest frame. So the further to the right you are, the stronger the emission line is relative to the surrounding continuum. This is just a histogram, and at low redshift this is in brown, and you can see that peaks strongly at low equivalent widths. But at high redshift you have quite a flat distribution, tailing off but going out to extremely high equivalent widths, in this case for the option 3 line. What is that saying? That says that on average, if you do a rest frame ultraviolet selection of these distant galaxies, which is how we select a lot of the high redshift targets for JADES, on average, their current star formation rate greatly exceeds the average of the past. So, i.e., they are very bursty. You're capturing them in a burst of star formation. So this left-hand plot, this is the fraction which have extreme equivalent width emission lines as a function of redshift. So very few at redshift 2, a few percent, going up to being half the population at redshift 6 or so. So this is the fraction of the population that's in this active, highly bursty phase. And we've looked at, with Jacopo Chevallard and other of my postdocs, what the previous star formation histories are. So this is a repeat of a very similar plot like I showed from Alex Cameron earlier on. These are where these very bursty high equivalent width galaxies sit. Again, typically high ionization parameter, typically low redshift. And we slice these according to the equivalent width of the emission line. As one would expect, at low equivalent width, these are the red line. A lot of the star formation activity happened in the past, more than 10 million years ago. You'd expect that. Effectively, that's how they were selected. The very bursty population, which dominates the numbers, it implies we're catching a very intense burst close to the epoch of observation within 1 or 2 or 3 mega years. So this is the orange shaded bits on the right of these two plots. This is how we would select these extreme equivalent width objects and how their star formation rates look, and how their luminosity-weighted ages look. So luminosity-weighted ages are young, 3 megayears or so. The ratio of the star formation rate in the last 3 megayears to much longer times, of course, that ratio is very, very high in the extreme equivalent width objects. So we've shown there, if you do a UV selection, typically you get very, very young stellar populations. Now, if that's true, and if star formation rate is very bursty, shouldn't there be a whole bunch of galaxies that star formation has turned off? Those galaxies don't disappear. They get fainter, certainly in the UV, but they don't disappear. Do we have evidence of them? The answer is yes from JADES. So this example here has a Balmer break. So the Balmer break is dominated typically by A stars, and that those would have ages of a few tens to a few hundreds of million years, whereas the emission lines are coming from things which are a few million years old. So in this example, we don't see strong emission lines. We see a Lyman alpha break. That's how it was selected. But we see evidence of a Balmer break. So this is an example of a galaxy where it had intense star formation up until a few tens of millions of years ago. Somehow that's got quenched, that's curtailed, and this is a paper from Tobias Lucer from JADES. We now have more examples of that at high redshift, where star formation has ceased. Now, we don't have many of these. The reason is we select and rest frame ultraviolet, and they get very dim very quickly once you turn off star formation. But another aspect of JADES is we did a separate subsample where we selected in brightness at much longer wavelength, at 4 microns. That's much more sensitive, not to this instantaneous star formation rate, but to the older evolved stellar population and hence stellar mass. So we have some examples here of Balmer breaks at fairly high redshift, and I have a new student now working on this. In my last 10 minutes or so, I'll switch to talking about Lyman alpha in emission. Now, right at the beginning of the talk, I told you Lyman alpha was rubbish, waste of time. It's resonantly scattered, it's absorbed. We thought we could get it from the ground. In very few cases, we could. Now, I'm going to come back and say Lyman alpha is great. So why is Lyman alpha an interesting probe? It tells you about the physics of the intergalactic medium. It tells you how optically thick the universe is to that line. Therefore, it's a probe of how ionized the intergalactic medium is. And my postdoc, Gareth Jones, also working with another postdoc, Ayush Saxena, have looked at Lyman alpha emergence in JADES. And Ayush made the discovery early on in the JADES data of a Lyman alpha line at redshift 7.3, which wasn't the highest redshift Lyman alpha at the time, but its equivalent width was very high. In fact, it implied that almost all the Lyman alpha you would expect to be created by reprocessing the ionizing photons was getting out, which is almost unheard of. At redshift 7, it meant that this galaxy had to have an ionized bubble around it. If it had neutral gas around it, that Lyman alpha would be killed. So Ayush's discovery of this Lyman alpha line, this is the extreme rest frame ultraviolet, and we confirm the redshift through the emission lines of hydrogen and oxygen at longer wavelength, was very, very interesting. Because we looked around it and we asked the simple question, is there enough stellar mass in this galaxy when that formed to provide enough ionizing photons to ionize a bubble of the order of 1 megaparsec around it, such that we could see Lyman alpha emerge unimpeded? Short answer, no. So what was going on? So we looked in more detail, and it seemed that there were a bunch of other galaxies with photometric redshifts, and in some cases spectroscopically confirmed around a redshift 7.3 around it. So it seems that this galaxy, remember redshift 7.3, that's before the traditional Gunn-Peterson effect kicks in around redshift 6. So this is an era early on in the universe where classically you'd expect no Lyman alpha. You'd expect the universe to be optically thick to that line. We'd found Lyman alpha very strong in emission, and we found that this galaxy here had a lot of friends nearby with very similar photometric redshifts. So almost certainly this is an overdensity where ionization proceeded earlier than the universal average. It got moving, and if you add up the stellar masses of these, yes, there is sufficient to then carve out an ionized bubble of size a couple of megaparsecs or so within a reasonable time. So that was interesting, and but you know, you look at that, and redshift 7.3, yes, that's a bit beyond the Gunn-Peterson trough detecting the quasars. Not so surprising, though, you know, early on. But we were pretty confident, you know, Lyman alpha, maybe we'll see it to redshift 8 or so, but not beyond that. And then a couple of remarkable things came along. We saw it out to redshift 10. Some work I led initially on GNZ11, which I'm going to come back to later on in the talk. But also, more recently, Joris Wittstock out to redshift 13. Now, this should be completely illegal. I mean, the universe essentially should be a slab of neutral hydrogen. No Lyman alpha should get out. It should be resonantly scattered and quenched. Somehow, redshift 13, you know, that's about half an hour after the Big Bang, or you know, 300 million years after the Big Bang. Somehow, you've locally produced enough ionizing photons, not only to power this line, but to carve an ionized bubble around it and make this non-resonant. So that was quite a remarkable discovery, which I think theorists are still struggling to fully explain. So Gareth Jones has worked on the oval statistics of Lyman alpha emission. So as you go to higher redshift, the fraction of galaxies which have Lyman alpha emission, of course, drops. So we see here a redshift 6, 7, 8, the fraction of Lyman alpha photons escaping drops as you go to high redshift. We can use that to constrain overall the neutral fraction of the universe. Now, there are a few caveats here, one of which, below redshift 6, it's observed that the Lyman alpha equivalent width, this is before the universe becomes neutral, grows as you go further back in time. So this is, again, a function of probably the ionizing environment early in the universe being harder, something, combination metallicity, perhaps IMF, driving more ionizing photons But then you fall off a cliff at redshift 6, and we understand that because the universe is typically neutral. I've shown you an example of one spot where it wasn't, but we can understand this cliff. And the shape of this cliff actually tells you the reionization history of the universe. So Gareth has looked at that, and here, a bit of a complicated plot, but this, our JADES points are here, and this enables us to put a point here on the neutral fraction of the universe versus redshift. So our JADES point is here. So the universe was about 60% neutral at a redshift around 7. So this is great because it's complementary to the cosmic microwave background probes. And in fact, it does rule out some scenarios of reionization history. So that's work done by Gareth Jones. In my last 5 minutes or so, I'll just talk a little bit about a quite remarkable spectrum that we obtained. So this is one of the early spectra obtained with NIRSpec through the JADES program. This is a redshift 10.6 galaxy. It was known as a candidate for over a decade, initially from Pascal Ouche in 2016, who got a spectrum with HST down the bottom in slitless mode. Now, Pascal was very courageous, and it turned out right, saying that maybe this continuum break, which was not widely believed at the time, maybe this was a redshift 10 galaxy. So compare the HST spectrum bottom left with our JWST spectrum at the top. So this is the range that Pascal was looking at. You can see, yes, his continuum break was correct. His initial redshift of 11.1 was incorrect, but you know, within the loose error bars. But we now have not only the continuum break, we have many different emission lines, crucially of different elements. So we're able to get the astrochemistry of this distant galaxy. So as I already mentioned, one of the early discoveries, and I was reducing the data as it came in. It was in 4 segments coming in overnight, UK time. And when I combined the first lot, I emailed my colleague Chris Willett on JADES saying, don't want you to get you too excited, but I see a blip. Well, first of all, the redshift was wrong from Pascal. Secondly, I see a blip which might be Lyman alpha, and Chris is like, no way, Andy, really. You know, redshift 10, I don't think so. And then the second lot of the 4 data sets came in, and the signal was added up at the blip, and he's like, yeah, you know, we need to get this out very quickly. This is significant. And we saw Lyman alpha in emission. Somewhat offset, somewhat redshifted compared to the systemic velocity. This you can explain through resonant scattering effects. And in this case, unlike Ayosha's galaxy at redshift 7, Lyman alpha is suppressed, and it's apparently redshifted simply because the absorption of the neutral hydrogen has eaten away the blue wing here. So that was very interesting. Also, I mentioned that we had many different emission lines of different elements. Now, this is key because each element acts as a clock. Carbon, nitrogen, oxygen, they're produced by slightly different processes on slightly different timescales in stars. So by measuring the individual element abundances, this gives us a window into the prehistory of this galaxy, specifically its star formation history. We measured the oxygen abundance, and no surprise in this galaxy, it's low, it's about 1/10 solar. Not that surprising at redshift 10. Clearly not population 3, we see these different emission lines. But something truly remarkable, when we looked at nitrogen, it seemed to have emission lines of nitrogen in the rest UV. Things I didn't immediately recognize. I had to go to my online table to look up what nitrogen 3, nitrogen 4 are, because we never see them in low redshift galaxies. And here we plot the oxygen abundance versus the nitrogen abundance for low redshift galaxies. They have a very nice relation, this sort of curve relation. GNZ11 sits up here, well away from the relation. So the nitrogen is very rich. Somehow nitrogen has become very enriched compared with oxygen in this galaxy. And it's not a one-off. Now there's about a dozen high redshift galaxies with this nitrogen elevated rate. Rather a lot of text, but I'll highlight the key points. So these rest UV lines of nitrogen are rarely seen in lower redshift galaxies. They seem quite common in galaxies which are compact beyond around a redshift of 9 or so. It's difficult to explain. Nitrogen traditionally need a couple of generations of stars to get. It's a secondary process. So something strange is going on. So Alex Cameron in a paper sort of went through, clearly it's incompatible with the long timescales typically expected to enrich nitrogen. So you need some other mechanism. Commented that it's quite similar to perhaps to Wolf-Rayet spectra. It might also be globular clusters in formation. This has been much discussed. So some globular clusters today also exhibit elevated nitrogen. And it's been pointed out, while in this particular case we might not be seeing a single globular cluster in formation, it might be related to the formation of globular clusters. Various people have looked at that. Alex has also looked at lower redshifts and nitrogen, and as you slice by redshift, it seems that there are galaxies which tend to separate from this lower redshift relation as you go to higher redshifts. So this might not be the exception at high redshift, it might be more typical. I'm running very out of time, so I think I will skip to my conclusions here. So JADES, we've been enormously successful. We've got over 5,000 spectra which you can download and play with, including probing the epoch of reionization. That's beyond redshift 6. We've been able to measure the physical properties in the interstellar medium. It was hotter, it was less metal rich, and with higher ionization parameters. We've spectroscopically confirmed galaxies out to redshift 14 for the first time, including unusual element abundances. We've seen Lyman alpha out to ridiculous redshifts, and this provides some theoretical challenges. And we've shown that the star formation is increasingly bursty at high redshift. I didn't get a chance to talk about the blue beta slopes, but I'd encourage you to download the JADES data, both the imaging, which came out last month, and the spectroscopy, which came out last October. Thanks very much for listening. Yeah, so we did look at that. We thought that the lensing potential meant that it would be less than a factor of 2 enhancement. Less than a factor of 2. I mean, there might be an effect, but yeah. Less than, that was, yeah.
Thanks, very nice talk.
Hey, Matt, yeah.
So I've got 2 questions, but maybe I'll just
Yeah.
on for now. On the redshift 13 Lyman alpha emission, so
Yeah.
present it as a puzzle. I don't think you got to any suggestions about why.
Yeah.
Is the case that could winds be involved somehow?
Yeah, so the missing piece of evidence is we don't have a systemic redshift for this because we don't see other emission lines. So what will be key is what is the velocity offset between Lyman alpha and lines which are not resonant, because that tells you something about the profile of the absorbing gas. Also, the ratio, if you had a Balmer line, it would tell you the ratio of Lyman alpha that actually gets out. So there are hopes that we would get a deeper spectrum and try and get that. Although many of our favourite lines shift off beyond NIRSpec. So MIRI is hard work; it's less sensitive. So I think it's fascinating. We need more information really to interpret it.
So you're mostly focused on escape fractions.
Well, that's the work that Alex, that Gareth Jones has done. Yes, yeah.
Yeah. So also you showed a plot where you have the carbon toxin
Yeah.
ratio as metallicity, and you have models or something with population 2.
Yeah. Models not from me. I hasten to add. Yeah. So I'd recommend taking a look at Francesco's paper where he doesn't develop the models himself, but he explains where they come from and how potentially you can get this elevated C over O, which is elevated above the regular models. So that's a puzzle. And he claims the way out, and it does seem to fit with population 3 supernova model. Yeah. Yep.
When you only have the automatic redshift, I was wondering if it's possible that a dusty galaxy, a lower redshift can mimic
Yeah.
a galaxy at higher redshift, and is that something that can be at all overcome?
Yeah, so with JWST, we're able to probe that at some levels. So there's always been a concern, if you have a red blob, it could be high redshift, it could be an evolved population, intermediate redshift, you're seeing the 4,000 angstrom rate, it could be dusty, or it could be embarrassingly a T-dwarf star in our own galaxy. So the spectroscopy actually enables us to tell between these scenarios. We're not able to get a redshift for everything, okay, so there's always a worry where we don't get a redshift. What is the true nature of that object? But we do have deep Balmer observations as well, so often we're able to rule out it being very dusty in some cases because it doesn't show up in the continuum. We also have MIRI imaging going out to long wavelengths, not very deep, but that enables us to constrain that. But you know, we do find some dusty galaxies out to rather high redshift, and we're also able to use H alpha, H beta to look at the Balmer decrement.
Yeah, so my other question, so you mentioned quite early on the value of Hubble short wavelength data.
Yeah.
So did we have a lot of that data in the can? Do we still have a lot of data in the can? Were we just lucky that Hubble lasted as long as it did? Or was this the point of risk? And this is an expensive telescope to be dependent on Hubble.
So for JADES, we looked at the goods fields, and the goods fields were imaged around 2004, 2003, with ACS in the optical. Later on, they were imaged again in the infrared around 2010, but that we don't need because we're able to go very much deeper. But I think you notice a lot of the big legacy programs that got time have been Cosmos, have been goods through us, have been various other of the Hubble imaged wide fields. And there is a reason for that. You don't want to start afresh. Yeah.
And we've got plenty of that going forward?
Yes. I think so. We still have, even in goods, we've hit a small number of the possible galaxies, a small fraction. At high redshift, we've hit many of them, but over the intermediate redshifts, yeah.